Hello, I'm Bianca.
And I'm Paloma, and you are listening to the Climate Press.
A podcast where we aim to bring together climate science with public understanding and action.
Welcome to the third episode of the Climate Press. Today we have Amanda Maycock, Associate Professor in Climate Dynamics, and Martyn Chipperfield, Professor in Atmospheric Chemistry, both at the School of Earth and Environment at the University of Leeds. Thanks for joining us today.
Thanks for having us.
Thank you.
So first of all, what is the ozone layer and why is it important for climate?
So the ozone layer can be found in a layer of the atmosphere that we call the stratosphere. That's between about 10 and 50 kilometres above the Earth's surface. So it's quite high up. It's the level at which aeroplanes fly. So when you look out of the window from a plane, you're looking into the stratosphere and you're looking out at part of the ozone layer. So ozone is formed in Earth's atmosphere, and specifically in this case in the stratosphere, as a consequence of the incoming ultraviolet radiation from the sun. So the ultraviolet radiation comes in from space, and that has the effect of splitting apart oxygen molecules that are present in Earth's atmosphere. So about 20% of Earth's atmosphere is oxygen, and that ultraviolet radiation divides up those molecules. That allows further chemical reactions to take place that form ozone molecules, and these reactions are happening in the stratosphere all the time. So the chemistry that is responsible for forming the ozone layer was discovered by Sidney Chapman in 1930, so it's been known about for a very long time. But hints that the ozone layer existed were known quite a long way before this, back in the 19th century. People were taking measurements of the sun, actually, from Earth's surface, and looking at the distribution of radiation that comes in from the sun to the Earth. And they noticed that there was quite a large portion of radiation that was missing, if you like, that you couldn't measure that at the Earth's surface. And this was the ultraviolet radiation. So one of the very important functions that the ozone layer plays for us on Earth's surface is that it absorbs this ultraviolet radiation, which would otherwise reach Earth's surface, and it's very damaging from a biological point of view. It can damage DNA, and plants and so on. So the ozone layer, which is present, I said, in the stratosphere, it's between about 15 and 35 kilometres. It's where the ozone layer it peaks, and it's absorbing this ultraviolet radiation. Now, the ozone layer, although it's extremely important for us, if you took a slice through the atmosphere and you collected together all of the molecules of ozone in that slice, and you brought all of those molecules down to the surface of Earth, so you change the temperature and the pressure of all those ozone molecules and squash them down to the surface, you would end up with a layer that was only just a few millimetres thick. So the thickness of a coin, typically, a few millimetres. So that doesn't sound like very much when you think about this vast layer, tens of kilometres above the surface, but in fact it has a very important role for us.
So talking about the ozone hole, what is the ozone hole and how was it discovered? Was it always there?
Yeah, the ozone hole is the hole in the ozone layer over the Antarctic. So it's not strictly a complete hole, but what it is a very large reduction in the thickness of the ozone layer over the Antarctic, which appears now every Antarctic springtime. So that's from sort of late August through to early October. So the Antarctic ozone hole was discovered really in the mid-1980s by ground-based observations made in Antarctica. So those observations started back in 1957 in the International Geophysical Year, where lots of global observations, long-term monitoring was set up. And it was a British Antarctic survey led by Joe Farman and his team, who were making these routine observations of the thickness of the ozone layer over the Antarctic. And they noticed that in the springtime, the ozone layer was getting thinner. And so the thickness really started to decrease from the mid-1970s onwards. And it became noticeable by the mid-1980s. And that is linked to the increase in chlorine and bromine in the atmosphere from our use of gases such as chlorofluorocarbons.
So what are the main gases and where are they coming from?
Okay, well, those gases, chlorofluorocarbons were used in aerosol propellants. They have a trade name of freons. They were used as the gases circulating in the back of fridges to remove heat from food. There were other chlorine-containing compounds such as carbon tetrachloride used in dry cleaning and so on. So these are gases which had various applications. They were discovered in the 1930s. They became more and more widely used for these applications. But it was in the 1970s when people first started to raise the alarm that these gases are very stable. They have no atmospheric fate apart from to be transported slowly up to the middle atmosphere, where the intense UV radiation breaks them down. They release chlorine, and that chlorine can then catalytically destroy ozone. So that work was published in 1974 by Rowland and Molina, and they later won the Nobel Prize for that publication. But in the 1970s, the models at the time weren't complete. We had an incomplete understanding of atmospheric chemistry.
But what is a climate model?
A climate model is a quantitative representation of interactions within the climate system. This includes the atmosphere, oceans, land surface, and ice.
And the models at the time predicted that although we were releasing this chlorine into the stratosphere, the impact on the ozone layer would be quite modest. So that's why, even though we knew we were doing it, i.e. releasing chlorine compounds, not much was happening in terms of policy because we thought any ozone depletion would be quite modest and occur at quite high altitudes. And that's why this discovery in 1985 of the Antarctic ozone hole was a real surprise and sort of turned the subject on its head and taught us a lot about understanding of models and how we should approach subjects like this.
How are those gases transported from the surface to the stratosphere?
Well, they're very stable in the lower atmosphere. They're destroyed by short wavelength ultraviolet radiation, and that's the radiation which is stopped by the ozone layer. So unless the gases get above the ozone layer, they can't be destroyed. So it's just the general atmospheric circulation, which in the troposphere involves rapid mixing. But then once in the stratosphere, the transport is very slow because of the temperature inversion in the stratosphere caused by the presence of ozone. Vertical transport's very slow, and it takes 5 years or so for air to be transported through the stratosphere from the lower stratosphere to the upper stratosphere.
So, as Martyn said, in the 1970s, the effect of these chlorofluorocarbons on the ozone layer was thought to be quite modest, and it was really the discovery of the ozone hole that made us realise that wasn't the case. The question then was, why is this hole forming over Antarctica in particular? And the reason for that is that there's a very special set of conditions that are found over Antarctica which aren't really found elsewhere in Earth's atmosphere. So what happens during the winter time over the polar region is that the air there becomes very cold and forms a vortex around the polar region. And that air is allowed to becomes quite isolated and contained over the pole and becomes very cold. Cold enough, in fact, that clouds actually then are able to form within the stratosphere over the pole.
So it's
so-called polar stratospheric clouds.
So it's like a belt, like a circular ring of clouds, right?
Yeah, it's like a sort of a cone, if you like, of air that's contained over the polar region, sits there during the winter time, and clouds then form within that kind of cone of air. And it's really the presence of those clouds in Antarctica which provides the special conditions that then allow the ozone depletion to become very severe and much larger than is found elsewhere in the atmosphere. So, for example, if you compare with the Arctic region in winter, so the North Pole, temperatures there also become cold, but usually not cold enough to form substantial amounts of these polar stratospheric clouds. Happens sometimes, but not nearly to the same extent as happens in the Antarctic every year.
Mm-hmm.
And so it's the presence of those clouds that then allow additional chemical reactions to occur on the surface of those particles in the clouds that leads to this formation of this very strong depletion of ozone and the ozone hole. And that's why it's really a special phenomenon that's found in the Antarctic and nowhere else on Earth.
Mm-hmm.
Yeah, in fact, these polar stratospheric clouds, they were missing from our models in the 1970s, which is why we failed to predict the ozone hole. They're very beautiful clouds. They've been well known by polar explorers. They're called mother of pearl clouds or nacreous clouds. And so people who had been to the poles knew they were there, but we didn't make the link that they were important for atmospheric chemistry. And so models didn't include them, and therefore we didn't have the chemistry on their surfaces, and therefore we didn't predict the ozone hole. Now we know that as well as being beautiful, they're also key to perturbing the chemistry of the polar region, and they drive the ozone loss.
What are the similarities and differences between the greenhouse gas effect and the ozone hole? Are the same gases involved?
Yeah, so by the greenhouse gas effect, we're talking predominantly about climate change at the Earth's surface, about warming of the Earth's surface that results from increasing levels of greenhouse gases in the atmosphere. And that's really a very different process from what we've just described in terms of how the ozone hole has been formed, which is predominantly through these chemical reactions occurring on the surface of these polar stratospheric clouds. For the greenhouse gas effect, what we're concerned with is gases in Earth's atmosphere that are able to absorb infrared radiation. So this is a different type of radiation from what we've just been talking about with ultraviolet. That ultraviolet is very short wavelength radiation. The infrared radiation, which is absorbed by greenhouse gases, is at longer wavelengths in the electromagnetic spectrum. Now, although they're quite different and the mechanisms are really distinct, there is actually some connection, if you like, between the ozone hole and the greenhouse gas effect and climate change, because it turns out that in addition to having this potential to perturb the chemistry in Earth's atmosphere, the chlorofluorocarbons are also very effective greenhouse gases. So they absorb very strongly this infrared radiation, which is being emitted by the Earth out into space. So the rising levels of those gases in the atmosphere through the 20th century that Martyn described not only contributed to the formation of the ozone hole and the depletion of the ozone layer, but they were also contributing to climate change by altering the energy balance of the planet. So those chlorofluorocarbons have contributed to climate change that we've observed to date. The contribution is smaller than the main greenhouse gases that people will probably be familiar with, such as carbon dioxide and methane, but it is still there. So controlling the emissions of those gases is not only important for the ozone hole and for the ozone layer, but it's also important for trying to avoid further changes to the surface climate on Earth and further warming of the planet.
It's being called an unprecedented display of international cooperation to protect the Earth's environment. The Montreal Protocol, signed today, aims at stopping the deterioration of the ozone layer in the atmosphere.
The Montreal Protocol on substances that deplete the ozone layer is an international treaty agreed on September of 1987 and designed to protect the ozone layer. this protocol has put in place control of the production of 99% of ozone-depleting substances. Hailed as a milestone for all people on our planet, the Montreal Protocol is considered the most successful treaty ever negotiated and implemented. So, what is the key of the success of the Montreal Protocol? Why do you think it worked, and why the current policies to tackle climate change are not working as they should be?
I think first it's important to sort of give a background to how it was signed. So the Montreal Protocol, like you say, was signed in September 1987. But it actually came out of something called the Vienna Convention in 1985, which predates basically the discovery of the Antarctic ozone hole. So following on from the Roland and Molina work that I talked about earlier in the 1970s, there was some general concern around the world that we were doing something, i.e. emitting chlorine compounds into the atmosphere without really fully understanding their consequences. And so there was some sort of unilateral action around the world to ban CFCs in certain applications in the late 1970s in countries such as the USA and Sweden. But nothing really major happened. But there were moves to look at this problem under what you'd call the precautionary principle, i.e. we were sort of doing something we didn't fully understand, so we should keep an eye on it. And that's led to the Vienna Convention, which sort of paved the way for the countries to meet and sign the Montreal Protocol. And actually it's very coincidental timing that the Montreal Protocol was signed in September 1987, which is exactly the same time when the real cause of the ozone hole was discovered by a campaign following on from Joe Farman's paper. But the two events are not really linked, and that's an important thing to emphasise, is the fact that the Montreal Protocol was going to happen even though we had not established that CFCs and chlorine was responsible for the Antarctic ozone hole. Why was it successful? It's because the initial signing of the Montreal Protocol was quite modest in its ambitions. It proposed quite small cuts to the production of just the major CFCs, with the proviso that if the science became stronger, those reductions could be strengthened in various amendments. And so countries around the world found it quite easy to sign up to this initial protocol because of the quite modest targets that were set. So that's one factor. A second factor is that the ozone problems caused by basically the industrialised world making CFCs and emitting them, not by sort of the undeveloped countries. And so understandably they said, no, why should we pay the price for a problem caused by other countries? And that's where the Montreal Protocol allowed for what's called the multilateral fund, where developed countries would pay into it and provide support for developing countries to make the transition to alternative compounds. And also there's a factor such as the science case was quite clear. It was a very sort of targeted problem. We could soon start to see ozone depletion happening. The compounds involved have quite specific causes. The cynic might say that chemical companies could see alternatives they could use or ways of avoiding, i.e. making aerosol cans without propellants and so on. So it's a combination of circumstances, I think, but the real key ones, I think, were the sort of the clear science case, the way the protocol was constructed to be initially quite modest and allow for strengthening, and the multilateral fund. And clearly in the later amendments, which are named after the cities where they were signed, such as London, Beijing, Copenhagen, the controls became much more complete. And as you mentioned, now we control around 99% of the likely production of these compounds.
I mean, if one compares the sort of actions that were needed to implement the Montreal Protocol, if you like, within the developed world, so Martyn's described how there was a sort of fairly specific set of industry that were producing these compounds and using them in various applications. And that's really where the emphasis had to be on in terms of transitioning to using other compounds that could perform the same purpose but didn't have this effect on ozone once they'd been emitted into the atmosphere. And that transition, I guess it's an ongoing process, but it's kind of taken place. For climate change and for carbon dioxide and methane emissions globally, our whole sort of global economy and operations have been built around this fossil fuel reliance for energy production and so on. So it's clearly a much more complicated problem to try and work out alternatives for how we can go about living our lives in the way that we currently do, but adapting things in such a way that we can reduce and, eventually stop altogether the emissions of these greenhouse gases. So that's the challenge that we now face. And it's interesting to hear from Martyn about the fact that the clear science case wasn't necessarily completely in place even at the time when the protocol was signed, whereas I think for climate change now we have a very clear science case, but there is still some opposition and some sort of people who are unwilling to, countries that are unwilling to kind of sign on to reducing their greenhouse gas emissions in a major way.
Yeah, I think maybe that's because with climate change, we'll need to take radical action, and that scares people. Whereas if you set a few easier targets, maybe it's much easier.
But perhaps you can see parallels with that sort of ratcheting approach that Martyn described for the Montreal Protocol and the subsequent amendments to the initial protocol. The protocols that we've had in place so far for restricting greenhouse gas emissions, the Kyoto Protocol, those ambitions in the first commitment phase were quite modest. So, you could see that as a first step on the way, I suppose.
I mean, it's worth saying that there were plenty of sceptics around for the ozone hole as well. So scientists had to be, very forceful and careful about giving a clear message, because there were, after 1987, there were still some people not willing to believe that the ozone hole was being caused by chlorofluorocarbons. But quite soon the science case did become so strong that no one could deny it, basically.
Well, thank you very much, Amanda and Martyn, for sharing your knowledge and insights with the Climate Press. It's been a great pleasure to have you on the show today. Thanks.
Thank you.
Thank you.
That's all for today's show. Thanks for listening. We hope you enjoyed.
Today we talked about the science basis of the ozone hole and the Montreal Protocol, a great example on how if fast action is taken, we can mitigate our impacts on the climate system. In the next episode, we will continue talking with Amanda and Martyn, and we will discuss the present and future of the ozone hole. Don't miss it! Today's music was written and played by Cecilia Nicole from the Leeds College of Music and Marcos Arribas and Paloma Trascasa from the University of Leeds.
Stay tuned for upcoming episodes and follow us on Twitter using @theclimatepress.
Please visit our website, theclimatepress.com. See you soon! And remember, make love, not CO2.